Here's all my work and answers for this one. Some tangent line stuff, and then finish it off with like a little related rate problem here. So it gives us a curve, gives us the derivative. It does a derivative for us there. It mentions use the tangent line to the curve at this point to approximate the y coordinate. So they give us a point. I'm going to take that point and I'm going to plug that into this first derivative right here for the x and y. This is a no calculator problem, very easy to do so without the calculator. So just plug that point into the derivative. Once you get the slope of the tangent line, you can do the point slope form, go y minus your y value equals your slope times x minus your x value. There's the equation of your tangent line. And then it says like the x coordinate is 3. All right, so we're just going to take 3 and plug that in place for the x right there. And then I just move that 4 over, and then this is the no calculator part of the test. So you don't have to do this. Like if it looks simple enough to simplify and you wanted to simplify it, you can. But you are allowed to just leave it like that. You could even gone up here as long as you find the slope of that tangent line and then do this point slope. You could take that 3 and plug that in there, and then just move the 4 over and just kind of leave it like that, like 4 minus that 4 over 19 times 3 minus 2. You could just move that 4 over and just kind of leave it alone. So there you go. So if it ever looks a little bit too crazy to do without the calculator, just leave the numeric value like that and they'll give us credit for it. All right, part B is talking about a horizontal tangent line. Part C is talking about a vertical tangent line. So remember, on a horizontal tangent line, the derivative is equal to 0. That's where the top is equal to 0. And for a vertical tangent line, that the derivative is actually undefined. That's where the bottom of the derivative would be equal to 0. So we're going to be working with this derivative guy. Now, part B says, as the line y equals 1 tangent to the curve, the horizontal line y equals 1 tangent to the curve. So when I saw horizontal tangent line, I was thinking, is the slope, the derivative, equal to 0 when the y is equal to 1? So if you take that derivative and set it equal to 0, a fraction is equal to 0 where that top part is equal to 0. And so that derivative is equal to 0 where the top of that fraction is equal to 0. That's at x equals 0. So we found that there's a horizontal tangent line where the derivative is 0 at x equals 0. And then they're saying, okay, is that the same spot at y equals 1? So if we know it has to be at x equals 0 and they're questioning y equals 1, we just need to check, is the point 0 comma 1 on that curve? So if I take this point 0 comma 1 and plug in 0 for the x and 1 for the y's into the original function, it doesn't, we get 5 is equal to 48, which is not true right there. So no, that horizontal line y equals 1 is not tangent to the curve there, okay? So there you go. Letter C is talking about at a point, is a line tangent to the curve at this point vertical? All right, so a vertical tangent. So I just took this point and I plugged it into the derivative and I got this. And that means it was defined. All right, so if you have a vertical tangent line, that means the bottom of this derivative would be 0. All right, that's an undefined slope. The slope of a vertical line is undefined, so the derivative would be undefined. So the bottom would be equal to 0. So since the derivative, that bottom is not equal to 0, that answer is also no. That tangent line at that point is not going to be vertical, since the bottom of that derivative is not equal to 0. That the bottom of that derivative is equal to 3. Okay, so it's not undefined. All right, and then letter D, when you start seeing language like this, all right, so it says the y coordinate is decreasing at a rate of 2 units per second. They're giving us dy dt. When you start seeing language like that, that means it's a related rate problem here. So I started with the original curve. They gave us a point. I wrote down my givens. They gave us a point, and they also told us what the dy dt was equal to, decreasing at a rate of -2, decrease at a rate of 2 units per second. And what's the rate of change of the x coordinate? That's in symbols, is find the dx dt. All right, so let's take the derivative with respect to time there. So I do a normal derivative, 3y squared. I did 0 y's there, so I tag on a dy dt. And then this is multiplying two things with variables together. You have to use your product rule here. So we're going to go first function times by the derivative of the second. Derivative of y with respect to time is dy dt. And then we'll go plus the second function. and then we'll times it by the derivative of the first. So the derivative of 2x is 2, but you're doing the derivative of x, this will tag on the dx dt, and then derivative of that number is equal to 0. Now, right here, you don't have to do any simplifying. They gave you the point. So everywhere you see an x, plug a 4 in. Everywhere you see a y, plug a 2 in. And then everywhere you see a dy dt, plug a -2 in. And so that's what I'm doing. I'll let you work through that arithmetic on your own there. So just be a little bit careful with that. And then you're just solving for the dx dt. That's, you don't know what that is, but that's what you're trying to solve. So I just got numbers for this, moved it all over, and then got the dx dt was equal to 10 units per second. Didn't really ask for units on this, so as long as we end up with that 10, but convince yourself that that's all a very doable problem there. And then just the key phrases on B and C, horizontal tangent line, vertical tangent line. We've done those earlier in the year. That's just where the top is equal to 0, where the bottom is equal to 0. We've done plenty of stuff with the equations of tangent lines and plugging stuff in, and that's a good related rate. We've done a lot harder related rates to that early in the year. Parasol.